Welcome to our video lesson for section 1.6, inverse functions. We're going to be evaluating functions and going through the process of finding inverses and verifying that functions are in fact inverses and what it just means to be an inverse. Let's get started. All right, so simply put, two functions are inverses if you can take each ordered pair of one function, reverse the xy, so you have yx, and get every point on another function. So let's kind of look at this. I have my first function here, f of x, and you see that I have the ordered pair 1, 2. For my other function, in order to be an inverse, it needs to be the exact opposite, which is 2, 1. And I can verify this for all of my points. So we have 3, 4, which becomes 4, 3, my second function. We have negative 1, 3 for f, which becomes 3, negative 1 for g. And then we have negative 2, 5 for f, which becomes 5, negative 2 for g. So let's kind of make this a little bit more formal. What it means to be inverse is my domain for my function f is my range for my function g. And my range for my function f is my domain for my function g. So domain and range for one function are flipped to be the range and domain of the second function. To verify that two functions are inverses graphically, what we're going to do is draw the line y equals x, goes diagonally through our plane here, and I'm trying to see visually, if I were to take one function and reflect it over that line, would it end up being the second function? And for two examples here, we can see that is definitely true. When I draw it for my second example, again, when I take one function, if I reflect it over that line, does it end up being the second function? And it definitely does. So this is a quick way to kind of see something is or is not an inverse. And it doesn't really prove it because we're drawing it and estimating, but we can get an idea of if it is or if it definitely isn't. Finding inverses algebraically is a little bit more challenging than doing it visually. What we need to do first is rewrite this. So I have y equals 2x cubed minus 3, because f of x is another way to represent y. Now what we're going to do is we're going to flip our x and our y values. So I have x equals 2y cubed minus 3. And finally, I want to try and get y by itself. So the first step would be to add 3 to both sides. Then I can divide everything by 2. And finally, I'm going to take the cube root. And what I get is a cube root of x plus 3 over 2 equals y. And that is going to be my inverse. Now there's a new notation we're going to be using for inverses. So we have cube root of x plus 3 over 2. And we're going to say that equals to f inverse of x. So this little negative exponent, when assigned to a function, is going to be the inverse notation we use. All right, guys, go ahead and test yourself. See if you can find the inverse for these three functions. And then also try using the new notation to represent the inverse. All right, go ahead and pause the video and try this on your own. All right, so here we see we have our answers. For our first function, the inverse, again, you can see with our negative exponent there to show that this is the inverse function, is going to be the cube root of x minus 7 over 3. For our second function, f inverse is going to end up just being x over 5. And finally, for a third example, we have f inverse is equal to x plus 4 over 2. Hopefully you guys did pretty well with those. All right, verifying inverse functions algebraically. In order to verify two functions, so we have f and g, are in fact inverses, what we're going to be doing is show the two following principles will hold. So we're going to be taking the composition and we're going to do it two different ways. The first time we do our composition is we're going to say f of g, and when we simplify that, we should get x. The second time we're going to flip the order and do g of f, and again we should get x. So if I take the composition for my functions both ways and I simplify them, each time I have to get x. Now it's important to note that each time we have to get x, you could get it one way and not the other way. And in that case, they would not actually be inverses. So we have to get it both ways for them to actually be inverses. Let's go ahead and apply this. All right, we have two functions here we're going to use to demonstrate verifying algebraically that functions are inverses. We have f of x, which is 2x, and then we have g of x, which is x over 2. All right, the first time we do this, we're going to do f of g. So I have f of g of x, which means I'm going to take all of g and plug it in where I see an x in f. All right, so I have 2 times x over 2. When I simplify those, I end up getting x, which is exactly what we wanted to get. The second time we do this, we're going to say, okay, now I want to do g of f. So we're reversing the order we're doing this. So now I take all of f and I plug it in into g where I see my x value. So instead of x, I have 2x over 2. When I simplify that, once again, I get x. And just to reiterate, we get x both times that we did our compositions. So we have verified that these two functions are, in fact, inverses of each other. All right, we have two more examples here. We're going to try and verify that they are or show that they are not inverses. This one's a little bit more challenging, but we can still do it. So we're going to start with doing g of h of x, which means I take all of h and I plug it in where I see my x. All right, so we have 4 divided by 4 over x plus 3 minus 3. All right, conveniently, these 3's are going to cancel out. So now I have 4 over x. And you guys might remember that dividing by a fraction is the same as multiplying by the reciprocal. So I'm going to cross it off and multiply by x over 4. My 4's will then cancel, and I'm left with a final expression of x. Okay, let's go and do this the other way now. So I'm going to say h of g of x, which means I'll take all of g and plug it in where I see that 1x. All right, so we have 4 over 4 over x minus 3, and then plus 3. Okay, so again, what we're going to do is multiply by reciprocals here with this first expression. So instead of 4 over x minus 3, I'm going to say that's 4 times x minus 3 over 4. And we have the plus 3 over here. Our 4's are going to cancel. So we're left with x minus 3 plus 3. The 3's cancel, and we are left with x, which is what we really wanted to have. So for both of our compositions here, we simplified them, ended up with x, which means we can say that these are inverses of each other. All right, when it comes to inverses, one of the root definitions is that the domain and ranges are opposites. And we can use that to our advantage here when we're trying to answer these questions using our table. So to begin with, we have a straightforward question, find f of 8. 8 is an x value. So if I want to find f of 8, that means I'm looking for the corresponding y value. And we can see that we have 8 here. Corresponding y value is 42, which means that our answer is definitely going to be just 42. All right, for our second question, we have f inverse of 47. So the way this is written is we're really trying to figure out what is the corresponding x value for a y value of 47. Looking at our grid, we see 47 has an x value of 13, which means my answer is going to be 13. And for our final question, there's two parts here. The inside expression here is f of 12. Now that means I have to figure out what is a y value that corresponds to 12. So if I look at my table, my y value is going to be 46, which means I can simplify this to be f inverse of 46. Okay, now what that means is I need to figure out what the x value is that corresponds to this. So going back to my table, 46 has the x value of 12. So I know my answer is going to be 12. Now it's no coincidence that that is our initial value. So f inverse of f of 12 is going to be just 12. And this goes back to one of our primary definitions of inverses, is f inverse of f of x is going to be just x. They essentially just cancel each other out, and they do here as well. So if you ever have f inverse of f of some value, or f of f inverse of some value, your answer is always going to just be that value. 1-to-1. A function is 1-to-1 if each element of f of x of the range is mapped from one and only one element x of the domain. All right, now what does that mean? Essentially, this means that every x value in the function corresponds to exactly one y value. And simply put, our function has to pass what we will call a horizontal line test. We're going to look at what makes a function 1-to-1 both algebraically and visually. So let's go ahead and get started with that. Algebraically proving if a function is 1-to-1. So what we're going to start is we're going to say, well, what is f of a and what is f of b? Which means we're literally going to plug in a and we're going to plug in b. We're then going to set the two expressions equal to each other, and we're going to solve our equation. And what we're hoping to get as our final expression is that a equals b. If we don't get that, our function is not 1-to-1. If we do get that, our function is 1-to-1. And what this means is by getting a equals b, we can't plug in two different x values to get the same y value. The x values actually end up being the same, which proves our functions have to be 1-to-1. All right, show that the following function is 1-to-1. Again, what we're going to do is first we're going to plug in an a, and we're going to plug in a b. So I have f of a is equal to 3a minus 5. And then we have f of b, which is equal to 3b minus 5. All right, now what we're trying to prove here is that if I plug in two different values, a and b, and I set the equations equal, a and b must in fact be the same, which means they're the same x value. So for my next step, I'm going to say that 3a minus 5 is equal to 3b minus 5, and I'm just trying to solve for my a and my b here. I'm going to add 5 to both sides, which gets me 3a equals 3b. Divide by 3 on both sides, and I get a equals b. And this is what we want. And what this means is if I plug in two different values into my function, they end up having to be the same value, or there's no way for them to be equal, which means there's only one x value assigned to every y value. Once again, we're going to show that the following function is one-to-one. So to do that, we're going to go ahead and plug in an a. So we get f of a is equal to the square root of a minus 2. And then we'll also plug in a b. All right. Next step, set our two expressions equal to each other. So we have the square root of a minus 2 is equal to the square root of b minus 2. We want to get rid of a radical sign, so we're going to square both sides. So we have a minus 2 equals b minus 2, and then if I add 2, we end up getting that a equals b. So again, what this means is if you plug in two separate x values, they end up having to be the same x value, or there's no way for the function to be equal. Now I had a horizontal line test. So a function y equals f of x is one-to-one if and only if no horizontal line intersects the graph y equals f of x in more than one point. So our graph can only cross once, or the function is not one-to-one. For example here, we have y equals x squared minus 4x plus 7, and note that it is definitely not one-to-one, because if we graph the line y equals 7, we have 2 points of intersection, 0, 7, and 4, 7. We can see them on our graph here. So all it takes is being able to draw one horizontal line to intersect your graph in more than one place to show it is not one-to-one. If you can't draw a horizontal line that does that, then your function is one-to-one. Let's look at some more examples here. All right, here we're going to apply the horizontal line test to see if the graphs are one-to-one or not. If you look at our first function, a, we have y equals x cubed. We have the graph down below. And I'm going to go ahead and draw a horizontal line here, do my best to make it horizontal. And I'm going to take this line and I'm going to basically just drag it. And every time I drag it, it's only crossing the line at exactly one point. So since I can't cross the curve in more than one point, this is definitely one-to-one. Let's look at our second graph here. All right, for a portion of our graph down here, we can see it's crossing exactly at one point. When I get here, we can see it's crossing at more than one point. We have 3 different points for most of the graph here, 2 at the very top, and then 1 again. So because of this area here, specifically this line drawn, we see it's crossing in more than one point, so it is definitely not one-to-one. Now again, all it takes is one horizontal line that crosses more than one point to show that the graph is in fact not one-to-one. But I can put this line anywhere I want in this region here to verify that fact and prove it's not one-to-one. All right, guys, that does it for our lesson here. Go ahead and get started on the homework, and good luck.